I'm sorry, I'm a little surprised. I thought I was 6, but that is fine, I guess. I'm flexible. All right, so so good evening, everyone. Tonight, I'd like to welcome you to see the invisible world 1 billionth of a meter in size. So, how big is a nanometer? Well, our fingernails grow 100 micrometers per day. A nanometer is how much our fingernails grow in 1 second. So since we are in Bayern, I have taken this opportunity to wear a dirndl, which does in fact illustrate a physics concept. Twirling the dirndl in a beautiful dance is a wonderful way to see a nuclear spin. And much like a dancer needs music, a spin needs a magnet to start spinning. So when we see this picture of the dancing couple, we know who is involved in this dance. We know the movements that form the dance. And we know something about where it is typically done or performed. So similarly, observing the dance of a nuclear spin gives us information about the type of atom it is, the kind of structure it is part of, and information about its environment. So I'd like to poll the audience here. How many of you have had an MRI scan at the hospital before? Wow, a good number of you. A lot of health issues here, I guess. So, many atoms have a spin, including the... I'm not very well practiced with the clicker. Including the protons in the water in your body, which is kind of hard to see over there. And this is exactly what this medical imaging technology is based on. So while this is an amazing technology, it does have its limits, and that is to get information from surfaces. So at surfaces, there are very, very limited number of spins. And while such a clean surface might make Mr. Clean very happy, it's not great for magnetic resonance. So why do we want to get information from surfaces anyways? Well, from solar energy to the interaction of drugs with your cell membranes, many things happen at surfaces or interfaces. So, is it possible to use magnetic resonance to get information from surfaces? Well, when you bring it down to the nanoscale, yes. So when you bring a detector or sensor very, very close to your spins, you can see the spinning of these atoms, even from the limited number of spins at the surface. And that is where a girl's best friend, a diamond, comes into play. So we all know that diamonds are formed under intense pressure and that it takes a very, very long time. Fortunately for us, we have just the environment, a laboratory. So beautiful, pristine diamonds are grown layer by layer using chemical vapor deposition. Then we add a thin layer of nitrogen only 5 nanometers away from the surface. And we form these sensors called nitrogen vacancy centers. We can use green laser to activate these sensors, and they fluoresce red light. The fluorescence is dependent on the spins around the sensor. So each NV sensor can see spins about a hemisphere with a radius as deep as it is. So to show what nitrogen vacancy centers, what our sensors can do, we chose to study a very special surface, aluminum oxide. And we form a single layer of molecules on the surface. These molecules contain very special atoms, such as fluorine. When we dissolve this molecule into ethanol, then add it to our aluminum oxide surface, we are able to see a growth in our fluorine signal. So remember, frequency is just the dance of our fluorine spins in beats per second. And we use arbitrary units for the signal size, which means don't worry about the units. So we can see this chemistry happening in real time. It's like being on the dance floor when the dancing happens instead of seeing it on Instagram. So after doing a little bit of math, we found out that our signal comes from 10 with 10 zeros behind it number of spins. In typical magnetic resonance, you need 10 with 12 or 15 zeros. So at the very least, bringing magnetic resonance down to the nanoscale makes you 100 times better at detecting spins. So now we've seeing signal from the small number of spins at the surface using nanoscale magnetic resonance. However, this technique has so far been limited to things like our layer molecules, which are like tethered to the surface. In the nanoscale world, liquid molecules move very fast. For example, a water molecule can travel 5 nanometers in only 2 nanoseconds, which is way faster than what our sensors can detect. It's like trying to see something when what you're trying to see is running like the Roadrunner from Wile E. Coyote. So when you have fast-moving molecules, you get a signal that is lower than what our sensors can detect. However, when you confine the molecules into a small area very close to your sensors, you can get a nice signal. And now I'd like to introduce you to a very nice porous material called metal organic frameworks. Metal organic frameworks, or MOFs, consists of metal nodes or centers connected by organic linkers. They have pore sizes that could be only a few tenths of a nanometer in size, which means you could restrict individual molecules. You could trap individual molecules in them. So we were able to grow a thin layer of MOF on our diamond. And here's where I have to confess, while SURMOF stands for surface anchored MOF, to me it represents how emotionally challenging surface science is. So here's our poor liquid molecules trapped in our pores. And we get a very nice signal from them. Without the MOF, we don't see anything. So, by confining, we can see that by confining our molecules into a small area, we can do nanoscale magnetic resonance on them. I hope you've enjoyed the night so far, and thank you all for listening.
Thank you, Kristina, very much. And please excuse my total confusion in the order. I was just staring on the upper line of my paper, and that was your line.